What's up, everyone? Welcome back to Make It and Break It. My name's Andrew, and today I don't know what series we're on right now. We're shooting a lot of stuff, but we're gonna go into why I think this broke and test it, just to break some more things. So, on the last Garage Build episode, or Garage Build episode 5, or whenever we were trying to see if this trolley would hold up to an engine stand, I took the place of an engine stand, stood on this engine trolley, and broke it mid-sentence. I thought this might happen when it was loaded this much, and there's a couple reasons why. And we're gonna go over some of those reasons with you right now, and then break some more 3D printed parts to hopefully prove that I'm right. So, I'm gonna pull these sleeves off here. These things are gonna be used to connect these two halves back again once we're done with this demonstration. But this is what happened when I stood on this, and there's a couple reasons for that. I think one, I had some control over, but there's no real control over it, is the material. So PLA is good at a lot of things and not so good at other things. PLA is very stiff, which means it doesn't like to bend. It has a high modulus of elasticity. That's essentially it's a measurement of how hard something is to bend or elongate. But once it gets past its essentially yield point, it has a very little elastic stretch, which means once it starts bending, it's pretty much going to break. It's very brittle. So when I was standing on the trolley and I said, hey, there's quite a lot of movement, what that says is, hey, this thing's gonna break because it's already bending quite a bit, and PLA does not have that much of a plastic deformation area, nor does it have a particularly long elongation before yield. The other reason is I was loading it wrong, or I think I was loading it wrong. So this material, this thing was printed basically straight up like this, which means the layers are stacked up like that. And it broke, see some of this, or maybe I'll get you some B-roll. It broke basically along the layer lines. It crossed over at some weak points in the build here, but it broke along the layer lines, which would be what I would expect for something that was bowing so much in the middle like this. However, when we were originally designing this trolley, we designed it with specifically not bowing that middle in, because we designed it to hold a transmission, not an engine block. And the transmission is long and thin, relatively speaking, and the width is designed such that all the weight would bear on the two cross pieces here and here. In that case, with the lines going like this, instead of loading on the weak point, which is the joint between the layers, you're actually loading on the strength, or you're actually loading on continuous strands of PLA, which should be more consistent and stronger than loading such that you're bending and cracking it between the layers, which is pretty much all the failures I've seen of PLA so far have been layer adhesion failures. So I was specifically loading it wrong, and it broke. I kind of wanted to test and prove that this is the case. I know there's been some scholarly work done on this subject, and I read some papers, which is kind of how I came up with my infill percentage here, although I did it wrong. I'll explain that in a little bit when I go through our test specimens. But there's not been a whole lot of testing done on bending stresses and relative capabilities based on print orientation and infill type and orientation and that sort of thing. This infill specifically makes this sort of break more susceptible. I'll explain that now when I go over what we're testing today. So here is going to be our testing setup for today. We have our test specimens. These are 3 identically dimensioned test specimens, but they're printed in different ways. So these 2 test specimens were printed on the bed plate like this, horizontally. What that does is that stacks the layers like this, and so one of them we're going to load exactly like that with all the layers stacked horizontally, and one we're going to load in what would be the ideal with the layers over top like this, and how we originally designed our how we originally designed this to be loaded. The third item, this one, was actually sat on the print bed like this. And so what that does is that stacks the layers this way. And what that means is then we're going to go load it such that the layers are in the same orientation as where our trolley broke on the garage build episode when we were testing it. And we're going to see which one breaks first, or what the relative breaking order is. This is not a scientific analysis. I'm not attempting to quantify the bend strength of these items, because these are not to any ANSI or ISO testing standard. But this is kind of for your information and for my information, because I have this whenever I've designed material, including stuff for you guys on this channel, I've always designed trying to keep continuous strands of plastic in the load directions. And I'm pretty sure that's the correct way to do it, but I also haven't read anything from anything I would consider reputable to validate that. So we're going to test that a little bit today. So we've got these 3 specimens, we got the test set up, and our load, and I don't know if it's going to be enough, but we're going to figure it out if it isn't. How we're going to load it is we're actually going to take a dumbbell. This is a workout variable weight dumbbell, and I've got one of my load slings here from lifting an engine, so obviously this will not break. We're going to hang it over the end here and load weights onto it. And when this one breaks, we'll figure out how much it breaks at, hopefully, and then we'll load the next one and the next one and see if the break weights are different. Hopefully they are. Hopefully these 2 break at higher weights, because then that means your orientation matters. When stuff is stranded like this and manufactured like this, I believe it behaves a lot more like carbon fiber and other materials like that, where there is an axis where the material is very stiff and very strong, and there's also an axis where the material is very weak. And so that seems to make sense in my head, but I haven't tested it, so that's what we're doing today. One thing I did promise you guys, I was going to talk about infill. So the way my slicing program works is it determines what direction the infill goes on these things based on the orientation of the bed's origin. So its 0 point is the front left corner, and then its standard infill on a grid pattern is at 45 and 135 degrees. So if this were the print bed, right? We got our print bed here. This is your 0. This would be 90 degrees, 0 degrees, 180 degrees. It infills at 45 degrees and 135 degrees. Hopefully that makes sense to everyone. However, because of the size of this piece, I actually printed it at 45. But I didn't change the infill angles. So what this thing actually printed at for infill, instead of printing infill along the face like in this direction and in this direction, and kind of bringing all the stresses together a little bit better, it actually printed straight across and straight across. Which means, it's very anisotropic. I think that's the word. It's been a while since I've been to school, guys. It made this entire thing very sensitive to load direction. Unfortunately, I caught that after I printed these, and I spent so much time printing this I wasn't going to print them again. So we're not going to get a true one-to-one test, but these items I printed straight at 0 and at 0, and obviously the one that's printed like this doesn't really matter, but it got printed at straight like this. So there's gonna be hatching in here in the fill that is different than the hatching in there. But the hypothesis here is that most of the stresses are carried in the surface layers. In this case, these have 5 shells or 5 surface layers before the infill. And so the infill orientation at that point probably doesn't make a difference if the hypothesis is correct, but we will find that out momentarily. So first up, we have specimen number 1 that was built vertically. Eyes on for safety, everybody. I kind of thought it would break earlier. Let's go find something. Now adding 1 gallon of distilled water, which is the same as regular water, but they put a fancy label on it. Toes out from under this. Let's go find what else we can put on here. £5 weight. 5 pound weight number 2. 8 pound weight. Table gave way. We're gonna have to try this again. Okay, so we got a new setup here. We've actually gone in and tried to clamp it in our vise here. See if that works. The reason I didn't do this the first time is because I built this to kind of hold it on the end. I didn't really plan on having this side take the weight. So we're gonna see how that goes. 25 pounds. 8 pounds, 5 pounds, another 5 pounds, another 8 pounds. Guess I should have made this weaker, huh? Oh, jeez. Okay, so we got our broken pieces here, and looking at them, it looks like, as kind of expected, they sheared pretty much right along a single layer here. Some of the support went a little both, but essentially the exterior layer is sheared along the one sheared. It broke on one particular layer, and then nothing else particularly. Well, you see we can see some of the high stress areas here too. There's some discoloration. You can see the corners. Yeah, see the corners there? Those are the higher stress. That's where it was plastically deforming. That's why the color changed. And then it gave way all of a sudden, and that's why those colors are different than the bottom. And you can see this has the same coloration problem. So, pretty cool. But yeah, it broke along all the layers of this, which is kind of how we think it would break. So now the next one is going to be the one that was printed horizontally, but it's not going to be loaded in what we call the ideal condition. So it's still going to be loaded like, it's going to have all the continuous lines running around the edge here. So these are continuous lines along this side, but it's still going to have some layer lines showing. So we'll see if this also breaks around the same way in time. All right, here we go again. 25 pounds. Interesting. Wonder if that'll change for the loaded on that side. Well, I'm not sure if I caused that one or not, but this one also looks like it broke along a layer line. In this case, because of the way we're testing it, it actually broke weaker, but I think it might have broke weaker. I might have just loaded it incorrectly, such that I gave it a shock load, where the other one I was trying to load it pretty nicely. But what happened here is really interesting. So you see this and this, see how thin this front layer is? Well, what happened is, and what happens in this scenario, if you have something holding you right here in this edge, your highest area of stress is going to be right in this corner here. And because of the way this is built, right in that corner, your highest area of essentially bending stress, and it's trying to tear apart the piece, is also where layers meet together. So this thing actually failed very early like this, because the type of stress that it was seeing was actually bending it apart like that in the highest area of stress. The other one, if we look at this piece here, this one also failed in a very high area of stress, right? So you have high compression or high tension up at the top. Engineering basics, if you bend something like this, on top it's going to be in tension, on bottom it's going to be in compression, right? So in this case it failed in tension, which is functionally where this one failed, at the highest area of tension. But this one, because of its configuration and the way we're loading it, this high stress area right here where everything is fixed, which is essentially going to be your highest stress, everything else has a little bit of movement. So you'll see your highest stress is where something is fixed and can't move. So this high stress area where it's fixed right above the jaw was actually in compression. And so what that means is that's not what's going to cause a separation. What's going to cause a separation is the tension up on top, and that needs a little bit more weight to get going, apparently. Or at least that's what I'm taking off this. This is not scientific. This is but that's very interesting. So we're going to go put this last one on and load it in the way that I usually design things to get loaded, and we'll see if that has a different behavior. All right, here we go, and we'll see how she goes. 25 pounds. £8. 5 pounds. 5 pounds. 8 pounds. Jug of water. You might notice this one's bending considerably more. It's probably going to break as I'm talking to you guys right now. But this one's staying bent considerably longer than the other two did. I have no doubt that we've passed its point of elastic elongation. We're into plastic deformation. Elastic deformation, plastic deformation. But this one is definitely taking much longer to break. I wonder what else we can throw on there to break this thing. RX-8 exhaust manifold. I'm not sure if we can break this with what we have here, but we have bent it and you can kind of see what's going on. So this is the bottom side where it was in the vise. You can definitely see where the vice's jaws are coming in on it, right in here. Let's see if we can zoom this in for you. So you can see where the vice's jaws are coming in and some of the deformation that's going on. You can see some of that there. You see that? But that was much more weight than we made with the, what I presumed would be more optimal version. Yeah, you can see some of the deformation there. That deformation is actually where it came out of the vise. So this started failing along a part line again, or a build line again, because that's the only way it could get out of the vise. So that is actually 90 degrees. You can see that. This bottom side here was down in the vise, and this side here is the one that bent. So you can see again, come on, focus. You can see again that these prints are failing at layer interfaces. But this one, because of the orientation of its layers, would take a lot longer to fail because you have to get some space for the layers to fail in some other manner. So that's kind of cool, and hopefully I'm not just confirmation biasing here, but it looks like I might actually be correct. Maybe. So one survived, and it's the one oriented like we've been trying to orient things, which is kind of cool. I'm gonna take these off now. No more need for safety, but that's actually kind of cool. This is not scientific. I would not call this, hey, orient all your prints like this because Andrew did it on Make It Break It, but that at least somewhat backs up our hypothesis that the weak points in a 3D print are the layer lines, at least in PLA. Some other materials might be different, to be honest, but in PLA it looks like the weakness of the print is actually in the layer adhesion itself, and that you can maximize your strength, at least, by orienting it like you would with carbon fiber, so that the lines of carbon fiber, the lines of plastic, are along the lines of your stresses, specifically your tensile stresses. So that's it for us today, guys. We had some fun breaking some plastic pieces and just bending them in some cases. And we also kind of validated my assumptions. That is that if you want to maximize the strength of your PLA prints, you want to orient the print lines in your direction, in the direction of the highest tensile stresses. If you treat it like carbon fiber, then you'll be fine. Which brings us back to this. Why did this thing break? Well, we made it out of a brittle material. You saw that in these breaks here. They were very sudden. There was not much elongation or stretching or necking down. Tough materials, materials that can that absorb a lot of energy, that stretch a bunch. Those materials do not behave like that under stress. And we are loading it along its weakest point, along its weakest axis. And when you do that, the print fails, as we've shown. It fails along the layer lines. Kind of an interesting science project here today. I haven't had a chance to do too many science projects like this in a while, so that's been fun. And hopefully you guys found it interesting and entertaining. I am a little depressed at my lack of weighted and calibrated heavy items. In order to get that last one out there, we literally brought in an RX-8 exhaust manifold. Yeah, thanks for watching, guys. If you liked this video, definitely hit like. Comment down below I'm really interested to hear if you guys want to see more of this experiment style of video. Do you want me to go test out the limits of materials? Because I can print basically any material outside of Peak and Ultem, so I can actually sit down and do the stuff I have a degree for and test the materials out for their strength. If you guys find that interesting out in viewership land, let me know in the comments down below. If you like what's going on in this channel, we're stuck in a little bit of workshop mode right now because I've got to get rid of the car that's in my garage. But when we don't have a car stuck in our garage, we have motorcycle projects. I got an adventure bike build out of an R6 going on. I've got an RX-8 race rally car build that we're going to be doing this winter. And more projects like that. Then check out our channel, watch the video, subscribe, and we'll catch you later.